So in our previous session, we have started with the BCD counter, how to design your synchronous counters, the steps we have seen, and how to design a 8-bit synchronous counter, that and all we have seen. And we have also seen how to design a synchronous BCD counter, what is the steps which we need, that and all we have seen in our previous session. Okay, so this was the circuit for our synchronous BCD counter. Okay, synchronous BCD up counter. Okay, and we have also seen that this BCD counter is going to count from 0 to 9 and it is going back to 0. Okay, so let me draw it one more time. Coming to this BCD up counter, this BCD up counter, the states it is going to count is it is going to start from 0 and it is going to 1, 8, 9 and it is coming back to 0. This is the state diagram for our BCD up counter. This we have already seen in our previous session also, and we have designed our circuit for this. Okay, let's say by if suppose our counter is in the state 10. Okay, it is not there in this particular state diagram. Let's say if our counter by mistakenly has entered the state which is known as 10. Okay, then what happens? Let me draw what is going to happen if my counter is in the state 10. So let me write down my outputs, that is Q3, Q2, Q1 and my Q0. Okay, and what is my next state? Next state is my Q3 plus, Q2 plus, Q1 plus and Q0 plus. And let me draw my T3, T2, T1 and T0. Okay, so this is my T3, T2, T1, T0 and Q3, Q2, Q1, Q0. What is my present state? Present state is 10. Let's say my present state is nothing but 10. That is 1, 0, 1, 0. Now, I don't know what is my, I need to find out what is my next state. Okay. So first of all, if I have my Q3, Q2, Q1 and Q0, I can get the values of T3, T2, T1 and T0. Okay. So how to get these values? So I will first of all write down the equations for my T1. So I will write down the equations here. T0 is equal to 1, we already know. And T1, which is equal to, I will write down from here. T1 is equal to Q3 bar into Q0. Q3 bar into Q0. This is my characteristic equations which I am writing down. Okay, and T2 is equal to Q1 Q0. Q1 into Q0 and T3 which is equal to Q2 Q1 Q0, Q2 Q1 Q0 plus Q3 Q0, Q3 Q0. These are my equations which I have derived in our previous session. So I will simply write T0 is equal to 1 and T1, what is T1? You can substitute the values of Q3 Q2 Q1 Q0 here. So Q3 is 1, that means it is nothing but 0. T1 is equal to 0. And what is T2? T2 is nothing but Q1 is 1 and Q0 is 0. So that's why it is also equal to 0. And what is T3? T3 it is equal to Q2 0. That means whole term will become 0. And Q3 is 1 and Q0 is 1. This is also equal to 0. Okay. So let me cross verify it one more time. T0 is equal to 1. And T1, coming to T1, what is the value of T1? Q3 bar. That means this term is also equal to 0. And coming to T2, Q1 is equal to 1 and Q0 is equal to 0. So T2 is also equal to 0. And coming to T3, here Q2 is equal to 0. This whole term will become 0 and Q0 is equal to 0. So this term is also going to become 0. So I have my inputs and my present state. I can write down my next state. If my T0 is equal to 1, then my Q0 is equal to 0, then my next state is equal to 1. I can write down. Okay. And if my T1 is equal to 0 and Q1 is equal to 1, then what is going to happen? It is going to hold the previous state only. Okay. And if your T2 is equal to 0 and your present state is equal to 0, next state is also equal to 0. Okay. And if your T3 is equal to 0 and your Q3 is equal to 1, and then what is your next state? It is equal to 1. So if my present state is equal to 1011, then what is my next state I am getting? It is nothing but 1011 I am getting, if you see carefully. Okay. Now let's say if my one more unused state is 1011. Okay. Let's say one more state is 1011. That is nothing but 11. Okay. By using the same method, let me find out first of all, let me find out the values of T3, T2, T1, T0, and from that I will find out the next states. Okay. Because I don't know next states, I have only this particular state diagram. I don't know what is, if my present state is equal to 10, what is my next state? I don't know. If my present state is equal to 11, I don't know what is my next state. So for this, I'm doing this particular calculations. Okay. So I already know T naught is equal to 1. Now, what about T1? You can substitute this Q3, Q2, Q1, Q0 values inside these equations and you can find out the T1. So what is your T1? T1 is nothing but 0. It is 1 complement, so T1 will become 0. And what about T2? T2 is also T2 is 1. T2 is 1 because here 1 and 1, right? So this is equal to 1. And coming to T3, T3 it is equal to, this term will become 0 and this term it is equal to 1. This is equal to 1. So these are my T3, T2, T1 and T0 values. Okay. Now what I am going to do, I am going to find out my next state. So if my T0 is equal to 1 and if my present state is equal to 1, then my next state it is equal to 0. And if my T1 is equal to 0 and if my present state is equal to 1, then next state is a hold state, that is 1 itself. And T2 is equal to 1 and if my Q2 is equal to 0, then my next state is equal to 1. And if my T3 is equal to 1, if my present state is equal to 1, then my next state is equal to 0 complement. If you see carefully, if my present state is equal to 11, then my next state I am coming to my 6. Can you able to see this? So if my present state is equal to 11, then my next state it is equal to 6. So from this I can conclude that if my present state is equal to 10, if my present state is equal to 10, then my next state is equal to 11. And after this, it is going to come back to this state which is nothing but 6. And it is going to 7, 8, 9 and so on. Is this clear? Can you able to see this? Now let us find out for other inputs also. Let's say our next input is 12. Okay. Let us find out the values of T0, T1, T2, T3. T0 is equal to 1 itself. And coming to T1. T1, how to find it out? Q3 bar, that is nothing but 0. So T1 is equal to 0. And what about T2? T2 is nothing but Q1 into Q0. Q1, Q0 are 0. And coming to T3, T3 is nothing but Q2 is equal to 1, Q1 is equal to 0. So this whole term will become 0 and Q3 is 1 and Q0 is 0. So this term will become 0. Okay. So these are my values of T and these are my present states. I can simply find out my next states. Okay. So if my T is equal to 1 and my present state is equal to 0, next state is equal to 1. T is equal to 0, present state is equal to 0, next state is equal to 0. T is equal to 0, present state is equal to 1, next state is also equal to 1, and T is equal to 0, present state is equal to 1, and next state is equal to 1. Okay, this is the state which I am getting. So if I am in state 12, then my next state is equal to 13. Okay. Now, let's say if my present state is equal to 13, that is 1, 1, 0, 1. Let us find out. So T naught is equal to 1 itself. And coming to T2, T2 is nothing but 0. T2 is nothing but 0 because Q1 is equal to 0, right? And coming to T3, it is nothing but Q2, Q1, Q2 is 1, Q1 is equal to 0. So this term will become 0 and Q3 is equal to 1 and Q0 is equal to 1. So T3 will become 1. Okay. Okay, I need to find T2 first. T2 is equal to 0 and T3 it is equal to 1. Okay. So this term, this is 1 and this is 1. Your next state is equal to 0. If your present state, if your input is equal to 0 and your present state is equal to 0, next state is equal to 0. Input is equal to 0, present state is equal to 1, next state is also equal to 1. Input is equal to 1, present state is equal to 1, next state is equal to 0. That means if your present state is equal to 13, then your next state is equal to 4. Can you observe? So here if my state is 12, if I am in my unuser state, that is nothing but 12, then what is your next state? It is nothing but it is equal to 13. And if my present state is equal to 13, then what is my next state? Next state is equal to, so like this, let us find out the next two also. And this is for 14, sorry, this is for 13. Let's find it out for 14 also. This we need to find out. And these are my T3, T2, T1 and T0. T0 is always equal to 1. And let us write down the equation for T1 and T2 once again here. The equation for my T1 is equal to Q3 bar Q0. Q3 bar Q0. Okay. So what is this is my Q3, Q2, Q1 and Q0. Q3 bar is 0, so T1 will become 0. Okay. And what is my T2? T2 is nothing but Q1, Q0. Q1 into Q0. What is your Q0? It is equal to 0, so T2 will become 0. Okay. And what is your T3? Here Q0 is equal to 0, so this term will become 0. I will write down here. T3 is equal to Q2, Q1, Q0 plus Q3 Q0 plus Q3 Q0. Here Q0 is equal to 0. So this whole term will become 0. Okay. That means my Q3 plus Q2 plus Q1 plus and Q0 plus I need to find out. What is my Q3? Q0. Q0 is equal to 1 and Q1 is equal to 1 itself because your input is equal to 0 and Q2 is equal to 1 itself and Q3 is equal to 1 itself. So if my present state is equal to 14, then my next state is equal to 15. Now, if my present state is equal to 15, let us find out the values of T3, T2, T1, T0 first. And from that, let us find out Q3 plus, Q2 plus, Q1 plus, and Q0 plus. So here T0 is 1 itself, and T1 it is 0, and T2 it is equal to 1, and T3 also it is equal to 1. Okay. So your Q0 plus value is equal to 0, and your Q1 plus value is equal to 1, and your Q2 value is equal to 0, and Q3 value is also equal to 0. That means if you are in your unused state, that is nothing but 14, so you are going to 2, right? Yeah. So if your unused state is equal to 14, then your next state will be equal to 15, and after this you are coming back to the state which is nothing but 2, which is a user state. So this is our BCD ripple count, BCD synchronous counter, synchronous up counter state diagram. Is it clear? Any doubts or any queries here? So that's why this BCD synchronous up counter, BCD synchronous up counter, this is known as your self-correcting counter. That's why it is known as your self-correcting counter. Self-correcting counter. Why it is known as self-correcting counter? If you can see from the state diagram, if for suppose let's say we are entering into some unused state, then after some time we are coming to the used state. If we are entering into 14, then we are going to 15 and we are coming back to 2. And let's say if we are entering into 12, then we are going to 13 and we are coming back to 4. And if we are, let's say suppose by mistakenly we are entering into 10, we are going to 11 and we are coming to used state. Okay, so that's why this particular BCD up counter, synchronous BCD up counter, it is known as a self-correcting. Now, not all the counters will be self-correcting counters. A counter will be set to a self-correcting counter. A counter is set to be a self-correcting counter if it enters into unused state. Then after some time it will come back to the user states by itself. Okay, then the counter is set to be a self-correcting counter. So this is about your self. So let us see about one more important concept using counters, which is known as sequence generators. Sequence generators. If I want to generate a random sequence, then I can use this counters for generating this particular sequence. Like let's say suppose if I want to generate a sequence 0, 3, 5, 6, 0, so on. If I want to generate this particular random sequence using this counters, using synchronous counters, then I can design this. How can I design? First of all, I need to draw the state diagram. Okay, so how to draw the state diagram? So let me draw the state diagram first. So the state diagram, the initial state is equal to 0, then it is going to 3, then this is going to 5, followed by 6, and it is coming back to 0. This is the state diagram of my sequence. Okay, so this is the state diagram which I am going to follow for designing my counter. Okay, now how many bits do I need? I need to decide. Now how many bits do I need for representing these numbers? Any idea? How many bits do we need for representing these numbers? Exactly. So why 3 bits? Because it is greater than 4. Okay, and so that's why we need 3 bits. So 0 can be represented by 000, and 1 is nothing but 001. Okay, 1 is not there. 3 is nothing but 011, and 5 is nothing but 101, and 6 is nothing but 110. Okay, Now, how many flip-flops do we need? Next step is to decide how many flip-flops do we need. How many flip-flops do we need?
Three flip-flops.
Exactly. So for n bits, we need n flip-flops. For 3 bits, we need 3 flip-flops. Okay. So I'm using a T flip-flop. Okay. I'm going to consider a T flip-flop because my design will be easier if I consider my T flip-flop. Okay. Now, if you want to follow a JK flip-flop or any D flip-flop, you can follow that. Okay. I'm going to consider a T flip-flop. Okay. For this T flip-flop, I'm going to draw the excitation table. Okay. So that is nothing but Q2, Q1, Q0 are my present states, Q2 plus, Q1 plus, and Q0 plus are my next states, and T3, T2, okay, T2, T1, and T0 are my inputs. Okay, so this is my excitation table of my T flip-flop. Now, if my present state is equal to 0, then what is my next state? From the state diagram I can refer. So it is nothing but 3. 0, 1, 1. Okay. If my present state is equal to 1, then my next state is equal to don't care because there is no state which is nothing but 1. Okay. And let's say if my present state is equal to 2, then there is no state like 2. Okay. So that's why my next state is equal to don't care. And if my present state is equal to 3, then my next state is equal to 5. Okay. So 1, 0, 1. And if my present state is equal to 4, then my next state is don't care because there is no such state like 4. Okay. And if my present state is equal to 5, then my next state is equal to 6. 1, 1, 0. Okay, I will write down here. And if my present state is equal to 6, then my next state is equal to 0. Okay, this is my Q3, Q2, Q2, Q1, Q0, and Q2 plus, Q1 plus, and Q0 plus. And this is my T3, T2, T2, T1, and T0. Okay. And if my present state is equal to 7, there is no such state like 7. So that's why next state is equal to don't cares. Okay. For this, let us try to write down the excitation tables. So T naught, we can see it is 1 here. And here in this case, it is don't care. And this case also it is equal to don't care. And here it is equal to 0. And here it is equal to don't care. And here it is equal to 1. Okay. Let's write the T2 also. It is equal to 1 here, and it is equal to don't care, and it is equal to 1, don't care, and it is equal to 1. And let us try to write down the T2 also. It is equal to 0, don't care, 1, don't care, and 0. Okay. And coming here, it is equal to 0 and don't care. And coming to T1, it is equal to 1 and it is equal to don't care. And here it is equal to 1 and it is nothing but. Now, what are the minterms for our T naught? If we try to write it down, the minterms for my T naught are 0, 1, 2, 3, 4, 0, 5. Yeah, only 0 and 5 are my minterms. And what are my don't cares which I'm going to get? The don't cares are 1, 2, 4, 7. 1, 2, 4, and 7. Let me check it one more time. 1, 2, 4, and 7 are my don't cares. And what are the midterms for my T1? T1 is nothing but it is 0 and 3 and 5, 0, 3, 5, 0, 3, 5, 6, 0, 3, 5, 6. And my don't cares are nothing but 1, 2, 4, 7. 1, 2, 4, 7. Don't cares will be same only for every thing. Sigma m. And what is my T2? T2 is nothing but it is 3 and 3 and 6. 3 and 6. And my don't cares are 1, 2, 4, and 7. So using this, we can plot the K-map and we can get the equations for my T0, T1, and T2. And from the equations, we can draw the required circuit diagram. Okay. And it is a 4 variable K. Total 16 number of cells. Q3, Q2, Q3, Q2, Q1, and Q0. Q1 bar, Q0 bar, Q1 bar, Q0, Q1, Q0, and Q1, Q0 bar. And this is my Q3 bar, Q2 bar, Q3 bar, Q2, Q3, Q2, and Q3, Q2 bar. So this is my K-map for my, let us write down the minterm 0 and 5, 0 and 5, and Don't cares are 1 to 4, 7. 1, 2, 4, and 7. So let us try to make the grouping. So I can, what I can do, I can group this. So I can form a quad. That's it. Okay. And no need to group this two. Okay. It will become a redundant. So my equation for my T naught, which is nothing but uh, Q3 bar and Q1 bar. T naught is nothing but Q3 bar and Q1 bar. Okay. So let us also find out the equations for T1, T0, T2 and T3. Let me copy this schemaps. So this is my equation for my T0 and let us write down the equations for my T1, T2 and T3. Okay. So coming to my T1 is nothing but what are the midterms for my T1? T1 is 0, 3, 5, 6. 0, 3, 5 and 6. Okay. These are my midterms of my T1 and don't care sir 1 don't care sir 1, 2, 4 and 7. 1, 2, 4 and 7 are my don't cares. Okay. So I can make a octet here. So my T1 is nothing but I'll write down here. So my T1 which is nothing but it is nothing but Q3 bar. Okay. T1 is nothing but my Q3 bar. Now let me write down the equation for my T2. So this is my T2. Okay. So what are the midterms for my T2? T2 is nothing but 3 and 6. T2 is nothing but 3 and 6 and remaining are 1, 2, 4, 7 are my don't cares. Okay. So I can group this 4. So what is my T2 which I am getting? This is my T2 which I am getting is what is the common terms? Q3 bar and Q1. This is my T2. So I've got the equations for my T naught, T1 and T2. Okay. So using these equations, I can draw a circuit. So let me draw the 4 flip-flops. This is my first flip-flop, second, third, and fourth. So this is T naught, T1, T2, and T3. Okay, I should find out for T3 also, right? T naught, T1, T2, and T. Okay, it is only 3 bits, right? So, and this is my Q naught, Q1, and Q2. And it is a synchronous circuit, so I'm going to have the same clock. So T naught, I can simply write it as Q3 bar, Q1 bar, Q3 bar, Q1 bar. So Q3 bar, Q1 bar, I'm going to give it to a AND gate, and this output is given to this input. Okay. And coming to my T1, T1 is nothing but Q3 bar, T1 is nothing, it is Q2 bar. Okay. And it is Q naught, Q1. Q2 bar, Q1. So where is Q2 bar? It is Q2 bar into Q1. Q2 bar into, this is my T1. And coming to T2, sorry, T1 is nothing but only simply Q3. And coming to T2, it is nothing but Q2 bar Q1. Q2 bar into Q1. So this is my sequence generator which is going to generate a sequence 0, 3 and 0, 3, 5 and 6, right? Let me check it. 0, 3, 5, 6, 0. Okay, so it is going to generate a sequence 0, 3, 5, 6 and 0 and so on. So this is how we are going to design a synchronous, this is how we are going to generate a sequence generators using our synchronous counters. Okay, is there any doubts or any queries here? And you can also check it whether this is self correcting circuit or not a self correcting circuit by the same method. Okay, you can substitute the values here and you can check it out, like if it is in a invalid state and if it is not coming to a valid state, then you can conclude that it's not a self correcting circuit. If it is coming to the valid state, then it's a self correcting circuit by the method which I have shown you, right, in the previous slides. You can follow that particular method and you can find it. We basically have f by 2 circuits, f by 4 and f by 8, so on. Okay, or else we have one more category, f by 3, f by 5, and f by 7, f by 9, so on. Okay, and one more category, f by 3, f by 5, f by 7, f by 9 with 50% duty cycle, and one more category, f by 1.5, f by 2.5, f by 3.5, so on. Here there is no nothing like that 50%. Okay, so this we need to have. Okay, and these are by default with 50% duty cycle by default. Okay, so this we are going to discuss. Okay, f by 2, f by 4, f by 8, f by 3, f by 5, f by 7, f by 9, f by 3, f by 5, f by 7, f by 9 with 50% duty cycle, and f by 1.5, 2.5, and 3.5. Okay, here we cannot achieve 50% duty cycle. Okay, so this is what we are going to discuss in the frequency divisions. Now first let us try to start with our f by 2. Okay, now, what is this F by 2 circuit? For achieving this F by 2 circuit, we have discussed it already. How many flip-flops do we need, and what is a mod counter which we need to consider for achieving a F by 2 circuit? So for getting a F by 2 circuit, we need a mod 2 counter. Okay, this we have already seen in our sessions. Let me draw it. So here we need a 2 counter. Okay, why do we need a mod 2 counter, and how the circuit is going to look like? That is all, that and all we have discussed in our previous sessions. Okay, let me draw it one more time. So for a mod 2 counter, how many flip-flops do we need? Any idea? For a mod 2 counter, how many flip-flops do we need? Okay, how many states a mod 2 counter is going to count? How many states it is going to have?
4 states.
No, it is going to have 2 states. Okay, a mod 2 counter is going to have 2 states. And basically a mod number is a number which is nothing but the number of unique states a counter can count. Okay, so there are only 2 unique states. Okay, and if you want to design a mod 2 counter, you can use a single T flip flop. Okay, this is nothing but our single T flip flop, T, Q, and Q bar, and you can provide one here, and you can provide the clock here. This is my mod 2 counter. This is my mod 2 counter. If you see, the initial state of Q will be equal to 0, and the next state will be equal to 1, and next state will be equal to 0, next state will be equal to 1. The number of unique states here, these are nothing but 2. Okay, so that's why it is a mod 2 counter. The mod number is equal to. Now, why it is frequency division by 2? Let us try to understand. Okay, so this is my clock. So this is my, let's say my flip-flop is working on the positive edges of clock. It is active on the positive edges of the clock. Now, let's say initially my Q naught is equal to 0. Okay, and my T is equal to 1 continuously. So my Q naught will be equal to 1 at the positive edge, and it will become 0. And again it will become 1, and here it will become 0, 1, 0, 1, 0. Okay, so this is my output waveform. And let's say my time period of my input clock is nothing but T. This is my T clock. And what is my output time period? This is my 1 cycle. Okay, this is the time period of my output. This is my T out. And if you can see the relationship between T clock and T out, T out is equal to 2 times T clock. Here you can see 2 times T clock. If you add, then you're going to get T out. Okay, T out is nothing but 2 times our T clock. And if you convert it into frequency, frequency is nothing but 1 by T out, 1 by T. Okay, so F out, output frequency is nothing but, it is nothing but 1 by 2 times of frequency of clock. So that's why it is nothing but frequency division by 2. So if you want to perform frequency division by 2, you can simply use a mod 2 counter. Okay. And if you want to perform a frequency division by 4, okay, then what type of counter you can use, what mod counter you can use? You can use a mod 4 counter. And if you want to perform a frequency division by 8, you can use a mod 8 counter. Okay, I will write down here. If I want to perform frequency division by 4, I can use a mod 4 counter. And if I want to use a frequency division by 8, I can use a mod 8 counter. Okay, this and all conclusions we have seen in our previous sessions. Okay, if you want, you can rewatch the recordings for this. So for a frequency division by 4, we can use a mod 4 counter, and frequency division by 8, we can use a mod 8 counter. Okay. Now, and we have also seen the conclusion. For frequency division by n, what type of counter we should use? Mod n counter we should use. For frequency division by n, we should use a mod n counter. Okay, this conclusion also we have seen. Now, if I want to have a frequency division by 3, if I want to perform a frequency division by 3, then what type of counter should I take? Here you can see the formula. F by n is equal to mod n. Okay. So what should be the mod counter I should take? Mod 3 counter.
Yes, sir.
So I should consider a mod 3 counter. Now for a mod 3 counter, what are the states I am going to have? I am going to have 0. So we should consider a mod 4 counter, and we should convert that mod 4 counter into mod 3 counter. How to convert mod 4 counter into mod 3 counter, that and also we have seen. So we have considered a mod 8 counter in our examples. We have considered a mod 8 counter, and we have used the clear signals, and we have made that mod 8 counter to mod 5 counter. Same like that only we should consider mod 4 counter, and using the clear signals we should convert that mod 4 counter into mod 3 counter. Okay, so I need to convert mod 4 into mod 3. Okay, then I will get a mod 3 counter. Now, so how this mod 3 counter is achieving f by 3, let us try to understand. Before that, uh, let me write down. So my initial state will be equal to 0 0, then next state will be equal to 0 1, next it will be equal to 1 0. Okay, so this is my q1 and this is my q0. Okay, I am going to consider my q1. I'm not going to consider my q0 output. I'm only going to consider my q1 output. Okay, here I'm going to get my f by 3 circuit. Okay, f by 3 frequency. Let us try to understand how we are getting it. Okay, so let me draw the clock now. So what is my q1 initially? It is equal to 0 0. It is equal to 0 0, and it is equal to 1. For two cycles, this is one cycle and this is second cycle, it is equal to 0, and next cycle it is equal to 1, and next again 0 0 1. I'm drawing my q1. Okay, I'm drawing my q1, not q0. I'm only drawing my q1. Okay, now let's try to find out the time period. What is time period? The time period is nothing but how many the number of the repetition after how much time it is going to take. It is nothing but it is one cycle. Okay, so the time, this is one cycle. For one cycle, it is, let's say it is taking t clock. Okay, this is one more t clock. This positive edge to this positive edge. This is t clock. Okay, for one cycle, let's say it is taking the time, it is nothing but t clock. T clock is nothing but the time, the number of cycle for completing one cycle. Okay, t clock is nothing but the time it is going to take for one cycle. T clock is nothing but time required for one cycle. What is one cycle? From this positive edge to this positive edge. Okay, and here what is the time period? So it is equal to 0 here, and again where we are getting the 0, again here we are getting the 0. Okay, so this is one cycle, this is one cycle. So how much time we are going to take for completing one cycle? We are going to take, let's say it is nothing but t out. Okay, I will write down here t out is a time, and if we can see here, if the clock is completing 3 cycles, then my output is completing 1 cycle. So I can write down T out is nothing but 3 times of T clock, because I can see from the diagram easily that if my clock is taking 3 cycles, then my output is being completed, then my output is completing only one cycle, then my output is only completing one cycle. Okay, so that's why my T out is nothing but 3 times of T clock. And if I convert this into frequency, then my frequency output frequency is nothing but 1 by 3 times of frequency of clock. 1 by 3 times of frequency of clock. Is it clear? So that's why we are saying it as a clock frequency by 3 circuit. Is this clear? Any doubts or any queries?
Yes.
Okay. Now, let us try to find out the duty cycle of this. What is duty cycle? Time period on by time period on plus off is the formula for my duty cycle. So what is the time period on? Time period on, how many cycles it is on? It is only on for one cycle. It is only on for one cycles. And T on plus T off is nothing but 3. 1 by 3 means, what is 1 by 3? I think it is 33.33. And if I convert it into percentage, it is 33.33 percentage. So this is my duty cycle. This is my duty cycle. So if I simply take a mod 3 up counter, then what is the frequency I'm getting? Frequency divided by 3. And what is the duty cycle I'm getting? And if I consider a mod 3 down counter, if I consider a mod 3 down counter, I will get a duty cycle of 66.66 percentage that I will discuss in the next session. Okay. And coming to F by 5 and F by 7, let us try to discuss. And after that, let us try to understand how we are going to design uh, frequency division by 50%. Okay, with duty cycle 50%, and then after we will discuss frequency division by decimal numbers. Okay, yes, so that's about the plan. Yes, so that's all about this particular session. If you have any doubts or any queries, you can discuss with me, or else you can leave the session. Okay, thank you.